To DC transference turns an AC current, a transformer, makes the AC turn into a DC. And a DC is like a battery, any battery, and a AA battery, AAA battery, D battery, any battery. Battery in your watch, battery in anything. The positive always sends the signal outward. The red is out, only out. There is no alternation here. It goes in one direction. And it goes through the system and then back into the ground. So it's a one-way cycle. So if I plug the red from the positive of the battery to this motor, it's going to spin. So that's a 12-volt DC motor that's spinning from this DC battery. DC, direct current, one way. Out the red, back in the black. So it's like a north only. I'm going to say a north only. It just pushes out the red and pulls in the black. DC. And I'm going to move on to show you how an AC transformer, which is in all of our electronic devices, changes the AC into DC, which actually acts like a battery. A transformer for a microwave oven. If you notice, you can see the AC comes in down here at the primary coil, red and black. So as the AC goes through, it goes in, out, north, south, north, south. And it makes the juice go through this primary coil in this way, and then charges the other way, and then out that way. So it goes back and forth, north, south, north, south, north, south.
So that means as the alternating current goes through the primary coil, it goes in one wire, around, and out the other wire. And then it reverses, goes in that wire, in and around, and back out the other wire. It does this 60 times a second. That's 60 cycles a second. It goes back and forth, north-south, through the primary coil. That correlates to the magnetic field it causes in the transformer core and in the air around it to do the same thing. As it goes one way, it pushes up, and it goes the other way, it pulls down. So that's north-south, up and down. And then when you put the secondary coil in the transformer core, it causes it to do the same thing. Up, and it goes out one wire, down, it goes out the other wire. Up, out one wire, down, out the other wire.
That makes the secondary coil do the same thing. These wires coming out of the secondary is out, in, out, in. The other one's doing the same thing, out, in, out, in. So it's up, down, north, south, north, south. So what I'm going to show you in a moment is I'll hook these two wires directly up to my 12-volt motor, and it's just going to hum because it can't go both directions at the same time. It can't go north, south, north, south, north, south like an AC motor does. So I'm going to show you that in just a moment. Notice I've got one wire from my secondary windings on my transformer, which I started down here and wound all the way up, all the way down, and all the way back up. There's 3 windings of this thickness of wire on my secondary coil. It's not touching the primary. The primary loops back and forth by itself, north, south, north, south, north, south, as the alternating current from my plug-in from the wall does that. As this secondary coil is energized from the static charge in the air from the primary coil, it does the same thing. It goes up, down, down. So the charge goes out one wire, out the other wire, out one wire, out the other wire. So it goes back and forth. Pulls in one, pushes out the other. Pulls in this one, pushes back out that one. Just like I showed you with magnets, how they do with a meter. So currently, I have one wire from the secondary hooked up to the ground of this 12-volt DC motor. I have the other wire hooked up to the other side of the transformer, secondary coil, and I'm going to use it as the positive. Now I want you to see what happens. When I touch it, it won't spin, it just hums. First, let me turn on the transformer. Transformer's running, Got power going to the secondary coil. When I hit the juice, nothing. It just flips the switch. There's too much contradiction in the direction. It's trying to go back and forth, out the black, out the red, back and forth, and it can't do it because this motor is only meant to go one direction. So in other words, right now the AC from the primary is going north, south, north, south. It's making the secondary go north, south, north, south. And as it goes back and forth, north, south, north, south, north, south, the motor doesn't know what to do with it. Because the motor it's a DC motor, it's meant to go only one direction. So I'm going to explain to you why or how these things are compromised or fixed with bridge rectifiers.
If you remember, I had an AC motor. It's an electric chainsaw motor, which is AC. Then here's my DC motor, which is just a starter from a riding lawnmower. I want to take a moment and show you about this AC motor that came out of an electric chainsaw, and it just plugs straight into the wall. That's how it's designed and made. The chainsaw broke down, so I kept the motor. But I wanted to show you how it runs plugged directly into the wall without a transformer to reduce the voltage. So when I turn it on, listen to the speed that it does off of just right out of the wall. Just wanted to show you that as opposed to what you're going to see or have seen with me hooking it up through the transformer on my secondary coil windings. It runs it much slower, but it's still AC. But I wanted to show you the intended use of this straight out of the wall at 120 volts, 60 cycles. But I've hooked my AC motor up to the leads coming directly out of my transformer, my microwave transformer, the secondary coil. I've got black to one and red to the other. What I want to show is, even though this is reducing the voltage of the AC back and forth, it will run that motor, but at a very slow speed. So that will run that motor because, like I said, as the primary coil's in and out, up and down, north and south, so is the secondary coil. Out one wire, back in that wire, and opposite out this wire, back in, back and forth, back and forth. This motor is meant to run that way. When one comes in, it pushes the motor, and when one goes out, it pulls the motor, but it always pushes and pulls in the same direction. So that's how AC works, back and forth, but AC induction motors use both push and pull to make it go one direction. A DC motor won't work with the pull, it only works with the push side. That's why it's DC, it doesn't alternate. So I wanted to show you how that motor that I used on my electric generating machine will work off of a DC transformer when it's the secondary coil is still running AC alternating current. It's not actually transformed to DC yet. It's just lowered the voltage. My next step will be to show you, as I showed you before, in the previous segment, the DC motor just hums when you hook it directly up like I did this AC motor. But the AC motor will turn on the alternating. So I'm showing the difference here of the two, AC to DC. Next, I want to show you how a bridge rectifier here will change the lowered voltage of the AC transformer into DC. Okay, now I want to show you how a bridge rectifier works on a smaller situation here after the transformer. We talked about how it's north and south, north and south. Even though we've dropped the voltage because of the secondary windings, it's still going out one wire, in the other, and then out this one and that one. It's going back and forth, back and forth. So what a bridge rectifier in this situation does, as the juice comes out this wire of the transformer, which is this red one, into the rectifier, it only lets that outward one go out the red wire to your motor. Then the other one, the white one, which will be pulling back when this one's pushing out, can only come in the black wire from your motor. And then vice versa. When this one's pushing out the white one, it's only allowed to go out the red wire. And The other one lets it come back to black one. So as these alternate back and forth, the bridge rectifier works like a gate, a double one-way street. It says either one of you that's pushing out has to go out the red wire. Either one of you that's pulling in has to come in the black wire. So in other words, the bridge rectifier turns this AC back and forth into a one-way street, out the red, back to black. That bridge rectifier turns the transformer basically into a battery. It's a one-way DC, direct current. And to prove that works, I'll turn the transformer on through the bridge rectifier to my little 12-volt DC motor, and it runs. Like I said, basically the rectifier has changed the AC, alternating which way it's going in and out these wires back and forth, to where it can only go out the red one and back the other way through the black one. It's like a gate, a one-way street out, a one-way street in, even though these two are alternating back and forth. This is a gate. That's how that works, to turn an AC alternating current in a transformer into DC, a direct current, which is what the rectifier does, to run DC motors. And it runs the DC components of TVs, microwaves, whatever has a direct current apparatus or components. Rectifiers and diodes are what direct it, where it can only go one direction, even though the current coming into the transformer is AC, back and forth. That's how it works. Tesla figured all this out years ago. We've just made it more intense, more power, more voltage on the AC transmission lines and on the apparatuses we use in our devices.